Hello, my name is Oscar Alvarez. I am from the University of Texas at Arlington. I am a PhD mathematics student here at UTA. I study under Dr. Chaokun Liu, which you've probably heard of if you know of Liutex. Dr. Chaokun Liu discovered Liutex here at UTA, and we will be calculating 3D Liutex in this video. Now, this is not going to be an in-depth explanation on how Liutex works. This will not be an in-depth coding tutorial. This is more of just a simple explanation on how to calculate Liutex. If you are trying to code Liutex in any application you are trying to use, I will be using Python. It's simple and easy to program in Python, and but you can code in Fortran, Python, C++, C, whichever language you choose. The method would still be the same. So on the right, I have a list of steps that we will be following to calculate Liutex in 3 dimensions. So this is assuming you have a 3D vector field of your fluid. Liutex is a vortex identification method. So if your fluid field contains any vortexes or any turbulence, Liutex is there to help you find it. So since you have a 3D vector field, you will have 3D velocity vectors. And the first step of calculating Liutex is finding the velocity gradient tensor, which is a 3x3 matrix. So the velocity gradient tensor, it's not really necessarily specific to Liutex, and it's calculated for other things like vorticity, which we also be calculating. So it's not really something you would specifically assign to this function that we're going to create. So we're going under the assumption that that you have the velocity data and that you have calculated velocity gradient tensor for wherever you are in your data. So let's begin by creating a function. I'll call it Liutex, and this is in 3D. And we're going to provide Liutex with the velocity gradient tensor. Velocity gradient tensor. Now, again, this is not an in-depth coding tutorial, so there are some things I could do to help optimize this code, like specify what each individual input is going to be and stuff like that. But for clarity, again, this is not for coding. This is more of just a step-by-step method of how to find Liutex so you can apply it. So the first thing we're going to do is take in the velocity gradient tensor. Now, I will be using NumPy because it is a library that has a lot of beneficial methods in Python. If you've used Python before, you've probably used NumPy. And it will have linear algebra libraries that we will use to find the eigenvalues and eigenvectors of matrices. So NumPy likes NumPy objects, so I'm going to turn our velocity gradient tensor into a NumPy array. So velocity gradient tensor. I'm saving it as A. So now that I have my velocity gradient tensor, I need to find the eigenvalues. So I need to find eigenvalues and eigenvectors of the velocity gradient tensor. So one reason I'm using Python, because it's so simple. NumPy has a library that will do this for me, but if you are, you find your own library to do it, or just do it by hand. So this function outputs the eigenvalues in a list, and it outputs the eigenvectors in a list. And I just use a NumPy's linear algebra library, find eigenvalues for my gradient tensor. Now, this is a very important fact or important idea of Liutex, is that if the velocity gradient tensor has complex eigenvalues, then there exists rotation. But if all of the eigenvalues of the velocity gradient tensor are real, then there is no rotation. So let's do that first. So if NumPy has a great method for this, is real object eigenval. So what's happening here is that this this will spit out a list of eigenvalues and a list of eigenvectors. Now, if the eigenvalues of this this matrix here are real, then all of the eigenvalues here are real, and this will be a real object, as in a real float value object. If this matrix has complex eigenvalues, then all of the eigenvalues will be complex. Now, it will be output like a complex value will have a real part. So this is like let's say 4, and then it will have an imaginary part. So let's say 5, say 2. So this is equivalent to saying 4 plus 2i, right? In this case, Python likes j for imaginary, but so this is the complex value, and then it's also stored as kind of a tuple as a 4, 2. So this is how Python holds these complex values. So we're testing to see if so test to see if eigenvalues are all real. So if they're all real, then we can stop. There's no rotation. So we can return our values. What we're going to do is we're going to return Liutex magnitude and Liutex vector equal to 0, because when Liutex is 0, there is no rotation. So the way this function is going to operate is, I'm just gonna, for the sake of brevity, I'm going to just copy from my notes that I have here, and so this function will calculate 3D Liutex magnitude and Liutex direction vector using the velocity gradient tensor, which is a matrix. It will return big R, which is the Liutex magnitude, and it will return little r, which is the Liutex vector. So when this function is going to return something, I'm going to return big R, which is 0, and I'm also going to return the vector, which I can make in a NumPy array of 0, 0, 0. So again, I know there's probably some things I could do to optimize this, but this is just for explanation of how to find Liutex. The next step is that we have to find, So if these eigenvalues are real, we're done. It will return and this will end. So we're done. We calculated Liutex. But if there are complex values, right? If there are complex values, then the function will continue past this. And we need to save a few things and extract a few numbers from the eigenvalues and eigenvectors. So we need to find the real eigenvector. So we have a list of eigenvalues and eigenvectors. So I'm going to see which one of these is the real one. So I'm going to loop through. So I'm going to say find real eigen value, or find location of real eigenvalue slash eigenvector. Now these are corresponding, so if the first eigenvalue in this list belongs to, it creates the first eigenvector in this list, and so on and so forth. So I can just loop through the eigenvalues and find the real one. So since they are all complex, I need to find the real one, and the real one has 0 for the imaginary part. So the way I'm going to do this is I'm going to loop through the list of eigenvalues. If the eigenvalue I that I'm looking at, and if its imaginary part is equal to 0, then that's my real. That's my real. So I'm going to save that index I. So if this eigenvalue is real, then I'm going to save that index. Now I need the index of the real eigenvalue. I also need an index for the complex for just one of them, one of the complex eigenvalues. And what I'm going to do, so complex index, what I'm going to do is I'm going to start from this index and I'm going to move over 1. Now in this list, so I'm let's say on the first index, and I'm going to move over 1. This will be complex. Now if the real value is at the very end, I'm going to move over 1, but that's going to be out of the list. So I want to start over at 0 whenever I move over 1. So the way I can do that is by doing a mod 3, and now if I go over the length of the list, which will always be 3, then I'll just start at the beginning, and that'll be a complex. So now I have the index of the real eigenvalue and eigenvector, and the index of a complex eigenvalue and complex eigenvector in the list. Again, this is very specific to the way that I'm writing this program in Python, but this still is a step. You need to identify the real eigenvalue and eigenvector and a complex eigenvalue and eigenvector. Now, now I need to get that real eigenvector. So real eigenvector is going to be, I'm going to go into the list of eigenvectors, and the way it's organized is that each row of this list is an entire eigenvector, and that each column is the corresponding eigenvector for the eigenvalue. So I want the entire eigenvector corresponding to the real eigenvalue. And I just want the real part. Again, these are complex objects, and I just want the real values of them. Because this is a real eigenvector, it's all going to be real. So I just want the real values, and this will give me a real list. So it'll give me a list of real values. So I found the now I need to find the complex eigenvalue. So this is why we need complex eigenvalue, and we call this lambda ci. So the reason I need the complex index is because I only need the complex part, say complex part of the complex eigenvalue. So because the way a 3x3 matrix works is that it will produce if it has a complex eigenvalue, then it'll produce two conjugate complex values and one real value. So there will only be one real value, and there will be two conjugate complex values. I only want the imaginary part of the complex value eigenvalue. So this is what we call lambda ci. So if you see that in the paper, that's what this is. And I'm going to go into the eigenvalues, and I want a complex index. I want the complex one. I want a complex eigenvalue, and I only want the imaginary part of that eigenvalue, which is what these two steps are. Now the next step is I need to find vorticity. Vorticity. Now, vorticity, you can either import it from whatever data you have if you already have solved for vorticity, but since it's so simple to calculate vorticity, then I will just do it here. And I just have the numbers written out. Vorticity, and it's calculated using the velocity gradient tensor. So let me type this in quick. Double check. Okay, so this is vorticity. I just initialized an empty numpy array and then put the values for it because vorticity is a vector. Now, we use vorticity to calculate Liutex magnitude, and we also use it to apply a condition. And so this is going to be the direction condition. So the condition is if the dot product of vorticity and the real eigenvector, if that is greater than 0, then our Liutex vector will just be the real eigenvalue, or the real eigenvector. And this copy is just I'm making a copy of the real eigenvector and giving it to R. Otherwise, so if this dot product is negative, then I will add a negative to the real eigenvector. So that will create. So this determines the direction of the of Liutex. Is the dot product between vorticity and the real eigenvector. So that was step 9. Step 10. We'll use the explicit formula to find the Liutex magnitude, and I have the formula written out here. W dot R, W is omega, and R is the R that we just calculated. So I think for the sake of room, I just kind of left it as W, because vorticity is often referenced as omega, which looks kind of like a W. So yeah, so now we'll find the Liutex magnitude. And to shorten this, I'll just in fact find vorticity, which is W. I'll calculate this first in order to save some room. Dot vorticity and R. And now calculate the Liutex magnitude R. And then now Liutex magnitude is equal to the dot product minus the square root of W dot R squared minus 4 times lambda Ci squared. Lambda Ci being the complex part of the imaginary eigenvalue. And that's Liutex magnitude. Now we finalize the calculation for Liutex vector. And that's just going to be R is equal to the Liutex magnitude times R. And we're done. All we have to do is return the Liutex magnitude and R. So return Liutex magnitude. Let me see if I can. Yeah, let's just copy this. Yeah, we're returning big R Liutex magnitude and little r Liutex vector, and we're done. So this is how you calculate Liutex in 3D in a 3D fluid field, flow field using Python 3. I'm using 3.11. I'm using NumPy. I'm not sure which version of NumPy, but this is how you would calculate it. And here are the steps, and I can post this under the description. So I hope this helps in you trying Liutex and seeing if it's a preferred method for whatever work you're doing. Thank you, and see you.